Good morning. Welcome back to our final session on microcontrollers in module 4. As you remember, in the previous class we were discussing about the architecture of microcontroller 8051. We have spoken about special features, all the different specific features of 8051. As shown, we have spoken about the 8-bit CPU registers, register A and B, that is accumulator and B register. A is used to store all operands of almost all operations in the CPU, and B is used only by multiply and divide. We have spoken about the 16-bit program counter and data pointers, both of which point to different memory locations. We have also spoken about the 8-bit program status word, which holds different flags which result from various arithmetic operations in the accumulator. And then we have spoken about the 8-bit stack pointer. The stack pointer usually was about, it was an 8-bit pointer which holds the memory address of the last filled location in the stack. Then we have spoken about the memory organization. 8051 has both internal and external memory. It follows the Harvard architecture. Accordingly, it has a 4 kilobytes internal ROM, which is used to store the program code, and 128 bytes internal RAM. Totally we said it would be 256 plus 128. So, around 384 bytes of internal storage, but out of that we just have 128 bytes where we have 4 register banks, each of 8 registers, and 16 bytes for bit stored or bit storable memory, and then 80 bytes of general purpose memory. And other than that, the upper 128 bytes are available for any general storage, which the addresses are shared in the upper 128 bytes by both the special function registers, SFRs we call them as well as the 128 bytes normal storage. So, we have 128 in the lower area, 128 in the upper area, and which is shared by two special function registers as well as general purpose memories. So, this is how we have discussed about memory organization. Then we have spoken about the 32 bits IO ports. IO ports we have in the sense 4 IO ports. Each IO port will be 8-bit in width, so totally 32 bits. Port 0 to port 3. Out of that, port 0 carries multiplexed address and data bus, whereas port 2 carries the higher byte of address, port 0 carries lower byte of address. Then we saw how the address latch enable pin is used to latch the lower byte of address onto the microprocessor, onto the latch. And then we have also discussed about port 1, which is a general purpose IO port, and finally port 3 where we have multiplexed control bus as well as data transmission. So, these were the IO ports which we discussed. Then finally, we have spoken about the timer registers, two 16-bit timers. Out of the two 16-bit timers, we have timer 0 and timer 1, both of which have 16 bits of data. So, both the registers have 16 bit of data, and each one can be addressed separately. Lower and higher bytes could be addressed separately. We saw we could have TH1, TL1, and we could have TH0 and TL0, higher and lower bytes of the timer. The use of timer was for generating waveforms or timing delays and to count events. So, this was the usage of timers. Now, let us move on to the full duplex serial data receiver transmitter pair, which is also commonly called as the UART. The other name for this is UART, which is a universal asynchronous receiver transmitter. So, UART stands for universal asynchronous receiver with transmitter, and this is the serial communication interface which we have in our 8051. What does it normally include? It includes serial communication which is made possible through the serial buffer, SBUF we call it as, serial port buffer, it is the short form for that, which is again a special function register. We have seen what it is anyway, and we will see again. And the next one is, we have two lines connected to this UART or the serial data receiver and transmitter pair. It is the TXD line which is used for transmission from the microcontroller unit. Any byte of data to be transmitted from MCU to peripheral is done through the TXD line, and then we have the RXD line or the receive line, which is used for receiving 1 byte of data from any of the peripherals to the MCU. The next is, we have two special purpose registers which are basically very useful for serial communication. They are the serial control register SCON and the serial port data buffer SBUF. These are the two special purpose registers or special function registers which are associated with serial communication. Then we have the serial port data buffer. This serial port data buffer is generally a special function register which has two registers in the same location. That means it has one register to used for reading the serial input data, another register for sending or writing into the serial port data buffer. So whenever I have to send out the data, I will use the register where I can write the data. The other one is to read the data, which is done using the serial port data buffer. So this is what I spoke of, two registers in the same location. One is read only, and that is called serial data receive buffer. The other is write only, it is called serial data transmit buffer. Next we will move on to the control registers or the special function registers in 8051. Some of the important SFRs are the timer control, also known as TCON, the timer mode control register, also known as TMOD, the power control register known as PCON, the interrupt priority IP, and interrupt enable IE. So these are some important special function registers, and we know what are SFRs. We have already spoken about SFRs in brief. So just to define again clearly, the upper 128 bytes of the on-chip RAM is used to house these special function registers. Though they share the same addresses with the upper 128 bytes of the general purpose RAM, in reality they have some specific functions allocated. In general, we have only about 25 such SFRs. Only 25 special function registers are used in practice. The other places were left vacant for further addition of new functionalities or new SFRs. So these are the registers associated with important functions in the operation of the microcontroller unit. Some of these registers can be bit addressable and some are byte addressable. Those that are bit addressable are also byte addressable. So they can be addressed as a byte in a whole or just as individual bits in the registers. So the address of bit 0 in that case will be same as the address of the register. These are the important special function registers. As you can note here, A or the accumulator is the first SFR which is used for all arithmetic logical operations. B is another special function register which is used for multiply and divide arithmetic operations. Data pointer high and data pointer low store the addresses of external memory where data is kept normally. IE is the interrupt enable register, which helps us to enable the internal or external interrupts, and IP is called interrupt priority. We can set the priority of the interrupt using this register, and P0 to P3, these four refer to the IO port latches, port 0 to port 3. Then power control register PCON, program status word PSW, we have seen all the flags of that register. SCON, the serial port control register. The SBUF, serial port data buffer. I told you that buffer has two parts, the receive buffer and the transmit buffer. Then the SP, stack pointer, 8-bit special function register, which holds the last filled location of the stack. Then timer counter mode control TMOD, then timer counter control TCON. Then we have the lower and higher bytes of the 16-bit timer registers, TL0, TH0 for timer 0, TL1 and TH1 for timer 1. So these are the most important special function registers which you need to remember and which we use commonly in the programming. The details of these special function registers, the symbols used, the expanded name and the addresses, that is where these special function registers are located, is clearly given in this. So it is not very clear, anyhow it will be there in the notes. Next we will see the specific features in terms of the interrupts. We know that 8051 has 2 external and 3 internal interrupt sources. What are these interrupts? So interrupts are just like in normal sense. What are interrupts? So you are doing some function and somebody comes in to the class asking for something else. So it is an interrupt. So what should the teacher do? The teacher should stop the class. He should address the person who has come, and whatever is their requirement, you should finish off that requirement, and later he or she should continue with the class. The same job is done in normal interrupts in the 8051. It allows parallel tasking in the sense the 8051 is already executing some program and it can just stop to whatever instruction it had executed. Say it had executed 10 instructions and another 10 were pending. It will just put a pause there after the 10th instruction. As soon as the interrupt comes, say the interrupt comes, then it will just go to wherever we have written a program which indicates what is the service required by this particular interrupt. Say I got interrupt 0, then interrupt 0 requires me to read in some data which has come from an input unit. So to read in that data, I would have written some code in some parts of the memory. So what does this 8051 do? It goes to that memory, it reads whatever code is there, it executes that code. That code is to read in the data, and once that job is done, it will come back to where it had stopped. It had stopped in the 10th instruction of the present program. It will come and continue with the 11th instruction of whatever it was doing. So that's how it allows parallel tasking. These interrupt service routine will run in the background in most of the cases. It is possible. It allows for a fast and low overhead interaction with the environment. So initially how these things were done? Say I have to take in data from some serial input device or some other input device. We would normally write a program called as polling program. What this polling program does? It remains in a continuous loop. In that continuous loop, it keeps on waiting for the data to be entered by the input device. So when the data is entered by the input device, it reads in that data, takes it to the memory location, and again it comes back to the same loop, and it will be continuously looping and waiting for input. Whenever input comes, it will read. So the CPU time is completely wasted. CPU is doing nothing else, but it continuously remains in the polling mode, waiting for the input to come. But now with interrupts, how this is avoided? The CPU continues with its job. It need not wait for the input to come. Whenever the input is ready, an interrupt will be sent by the input device. So as soon as the CPU receives the interrupt, it goes and services, it reads in that input data and it will come back and continue with whatever task it was doing. So, no need of polling and immediate reaction is there for the interrupt. If the CPU time is efficiently used, it is not wasted by remaining in a continuous loop waiting for something to come. It is an automatic function call, so very easy to write the program for interrupts using interrupts. 8051 has 3 internal software interrupts and 2 external hardware interrupts. The serial port interrupt is one of the software interrupts. It is just a wake up interrupt given to the CPU, informing the CPU whenever there is data arriving on the serial port or data moved out of the serial port. So, if CPU writes some data into the serial port buffer and the serial port buffer has to send it serially to the printer. So, as soon as the data goes out and to the printer, then the buffer is cleared, and once the buffer is cleared, it will inform the CPU that data has been sent out. Similarly, if the input device like a keyboard has put in some data into the buffer, the interrupt will be given, this serial port interrupt. CPU will stop its current job, it will come and read in the data from the buffer, and once that is done, it will go back and continue with its program. This is one of the software interrupts. Timer 0 and timer 1 overflows are the other 2 software interrupts. What do we mean by overflow of the timer? That means timers are 16-bit registers. We know that timers are 16-bit registers, and if the maximum possible value in a 16-bit register is all ones, which means FFFF in hexadecimal. So, the maximum possible value would be FFFF, and so as I was telling, FFFF would be the highest possible entry in the 16-bit timer. Now, if there is the next count after this would be 10000. This would be the next count. So, the 16-bit value, each of them is 4 bits. So, totally 16-bit values would be this 00. There is a overflow, the number has gone out of the 16-bit register. This indicates the overflow interrupt. So, if timer 1 has counted up to the maximum count, so this is the maximum count, it has counted up to the maximum count, and once it goes to the next count, or automatically this interrupt timer 1 overflow or timer 0 overflow comes there. So, other than this, we have the external interrupt 0 and external interrupt 1, which are hardware interrupts. We have the interrupt vector table, which gives me the addresses of the interrupt service routines. So, many times we consider reset as one of the interrupts. As soon as we get a system reset, where does the CPU control go? The CPU automatically goes and searches in the memory location 0000. So, what should happen on reset? That program should be written in this memory location. So, it means to say all these vector addresses indicate where the CPU control shifts to as soon as this particular interrupt arrives. So, as soon as we get a high on this particular interrupt, the CPU control goes to the memory location 0003. There we should have written some instructions about what the CPU should do when this particular interrupt arrives. So, the same thing, we have different addresses for the different interrupts. The last part or the last feature of 8051 is the oscillator and clock circuitry. As we know, between pin 18 and 19, we have a crystal of 11.0592 megahertz connected. So, between pins 18 and 19, a clock is generally used to synchronize all the operations of the MCU. So, when all operations of the MCU should happen in synchronism with one particular master clock, and that master clock depends on the crystal which we connect between these two pins, extel 1 and extel 2, which is pin 18 and 19, and the value normally for AT51 is 11.0592 megahertz. Other than this, we can use a TTL oscillator also, but normally it is the crystal which would be connected. Some microcontrollers use more than one crystal also. So, some operations are controlled by one clock, the another set of operations will be controlled by another clock. So, this is about the oscillator and clock circuitry. Finally, we have to see what is bus control. We know what is a bus. A bus is a collection of wires put together so that they can carry data from one point to another. So, wherever you plug in the bus. So, normally I will have an 8-bit data. So, I will connect all 8 wires together in a bus. Similarly, 16 bits of address, all the 16 bits could be connected. So, basically bus control or bus signals are those which arbitrate the data and address along with control signals between the CPU and the external memory. So, normally we have an 8-bit bidirectional data bus in the microcontroller unit AT51. Port 0 normally provides or carries data whenever we have to connect external devices. Then we have a 16-bit address bus. The lower 8 bits are multiplexed with port 0 and upper 8 bits are provided in port 2. So, whenever I have to address an external memory or external device, I need a 16-bit address. We already saw during the first few clock cycles, the lower 8 bits will be carried on port 0 lines, and then we will use the ALE, address latch enable pin. We will latch on this lower byte of address on an 8-bit latch, and then the same port 0 lines will start carrying data, and the higher byte is continuously available on the port 2 lines of the microcontroller unit. The control bus is multiplexed with the port 3 lines. It can have different control signals like read, write, program store enable PSEN, address latch enable and EA external access. The bus architecture of a microprocessing unit shows separate address bus, separate data and control bus. In a microprocessing unit, very often we have lots of hardware pins available. So, all this can be available as separate units. But in a microcontroller unit, the internal bus is common. You can see we have common internal bus connecting all the devices which are there on the same chip, and for external operation we will use the port lines port 0 to port 3. So, port 0 will carry lower byte of address for some time and then data, port 2 will carry higher byte of address, port 1 is exclusively for IO data transfer, IO operations, input output operations. Port 3 is also multiplexed with control signals. So, these pins or these lines are used in the microcontroller unit to save on the hardware. Other than this, we have 2 more pins. You need to connect VCC or a power supply to the microcontroller. Normally 5 volts is sufficient, and the ground pin, which is pin 20. So, pin 40 is the VCC and pin 20 is the ground. So, this completes our detailed discussion of the AT51 microcontroller. The summary is, we've spoken about all the features in detail and the architecture of the AT51 microcontroller, including different registers, the IO ports, memory organization, timers, interrupts, bus control and the clock circuits. In detail, we've spoken about all these, and we've also had the detailed description of architecture of MC8051. The last part of this module is the stepper motor interface. So, what is a stepper motor? Generally, we've heard about 3 different types of motors. You have the stepper motor, the DC motor and the AC motor. So, why stepper motor is different? Stepper motor has the rotating shaft moving in steps. It doesn't move continuously, but it moves in small angles or steps, and we can have control on that step size. How many steps should be taken for one revolution, by how many degrees one step is varied, so on. So generally, what is a motor? A motor is a device which translates electrical pulses into mechanical motion. So movement, all electrical pulses will be, electrical energy is converted to mechanical energy, especially here we convert it as rotational energy because we rotate a shaft. So the types of motor, as already mentioned, stepper motor, DC motor, AC motor. A stepper motor is a special type of electric motor which moves in increments or steps or angles rather than turning smoothly as the conventional motors. So typical increments or angles are 0.9 degrees, 1.8 degrees, 3.6 degrees, so on. So depending on that angle, we need to cover 360 degrees for one complete revolution, which means if the angle is 0.9 degrees, you will need to design for 400 steps. The rotor should take 400 steps to complete one revolution because the angle is small. If the angle is changed to 1.8 degrees, then the rotor needs to take 200 steps to complete 360 degrees or one revolution, and if the angle is 3.6 degrees, then only 100 steps are sufficient, so on. The speed of the motor. So generally in a motor we are interested in the speed and the torque. So the speed of the motor will be decided by the amount of delay which we are going to fix in the program. So we can consider the incremental steps, whether it should happen very fast or whether there should be some delay associated with the motor moving in steps. So speed in, we normally define the speed in revolutions per minute, RPM, and it will be decided by what delay we are going to set. We have two types of stepper motor. So before going into how to interface this stepper motor to 8051, we should understand what is a stepper motor or how it works in detail. So let's see. The types of stepper motor are permanent magnet stepper motor and variable reluctance stepper motor. In this unit, we are going to speak about the permanent magnet stepper motor. As you can see in this diagram, we have a rotating shaft at the center with the gear-like device or the teeth. There are teeth mounted on the rotating shaft, and then we have the covering that rotating shaft, you have the stator, which is going to have what? 4 poles or temporary magnets. All these 4 are 4 temporary magnets, and the rotor or the shaft is a permanent magnet. That is why the name permanent magnet motor. So this permanent magnet stepper motor has the rotating shaft in the center using a permanent magnet, and the stator poles will be temporary magnets. In the sense, how do we make temporary magnets? We are going to use windings. We are going to use copper coils wound around the stator poles. So whenever you send a current in that copper wire, this becomes, or the stator pole gets energized and it acts like a magnet. So you are creating a magnetic field from electric field by, you will surround the iron core with a copper wire and you will send current through that wire. So whenever you send a current through that wire, that pole gets energized and it starts behaving like a electromagnet, a temporary magnet. If the current is removed, then that magnetism is removed from the stator pole. So that is what I was telling, these 4 are temporary magnets. So the motor moves every time an electrical pulse is received. You can see pulse 1 and pulse 2, 2 opposite poles of the stator are connected to pulse 1. The other 2 opposite poles of the stator are connected to pulse 2. So current flows through these, helping it in moving. So, we can control the movement, both the direction of the movement of this rotor or the rotating shaft and also by how much it moves, the amount. We can force the motor to hold some particular position against an opposing force. How it is constructed? As I told you, it uses a permanent magnet rotating shaft or the rotor, and the stator is the one surrounding the shaft. It is usually, there will be 4 stator windings which are paired with center tapped common. Such a motor is called a unipolar stepper motor or a 4-phase stepper motor. So, as you can see here, these are the stator poles which will surround the rotor or the shaft. So, we have a central shaft, surrounding that we have the gear teeth like mechanism. So, this whole unit becomes the rotor unit or the shaft, and this will be present inside these stator poles. So, this is known as, since we use 4-phase excitation, it is called a unipolar stepper motor. You can see what are the, how the coils are connected. You have between A and B, we have the center tap or the common, and between C and D the center tap or the common. So, as you can see, if I consider this as A, the upper one as A, the bottom one will be B. So, I will use windings surrounding this pole A, and B will be the winding surrounding the bottom pole. Between both you have a center tap which could be connected to a power supply of 5 volts. Sometimes it could be grounded. And similarly, if I call the leftmost one as C, I will have one coil surrounding this C and another coil, the rightmost one is D, another coil surrounding this D, and between these two this common point will be taken, which both these common points will be connected to plus 5 volts power supply, as I will show you later. So, now it is shown here, see A and B up the topmost and the bottom one, C and D the leftmost and the right one. So, we will see this central one indicates the rotor or the shaft. So, initially I will call this as the unstable condition for the rotor, because of the coils used with the stator, you can see how these electromagnetic poles are created. This A has the north pole, again D has the north pole, whereas C and B are having the south pole. So, how the magnetism is created? A and D north, B and C south. So, now what happens? What is the general property? We know that like poles repel each other in magnets. So, the central rotor cannot be in this position because its north facing north will repel. It can't remain in that position, and south facing south, it will surely repel. So, what does it try to do? Opposite poles will try to attract each other. That means this south pole should come and sit facing the north poles. So, since there are 2 north poles, the south one should come and sit in between both. As you can see in the second figure, the south pole has come exactly to the center of these 2 north poles or of the electromagnets in the stator, and the north pole has come to a position in the center of the 2 south poles of the electromagnets C and B. So, now A, B, C, D all have the windings or coils, all of them are energized in such a way that the north poles are created here at A and D and south poles at C and B. Then the stable condition of the rotor will be something like this. It will settle in such a way that the south pole comes in between the 2 north poles of the electromagnets, and the north pole of the permanent magnet will come in between C and B, the south poles of the electromagnets. So, the rotor will always seek this stable position. Let us see now what types of excitation can be given to the coils. We can excite one coil at a time. It is known as single coil excitation. Every single coil is energized one after another. So, you can see here coil 4 is energized first, then coil 3, coil 2, coil 1. You can see in this diagram clearly how one by one the coils get energized. That causes the rotor to move accordingly. Similarly, I can have a 2-coil excitation where 2 coils are energized together. You can see coil 4 and coil 3 are both on, coil 2 and 1 are off. In the next clock pulse, coil 3 and coil 2 can be on, the others off. So, it goes on shifting. At any point of time, 2 coils will be on simultaneously. That was the condition which we considered while explaining how we get a stable position in the rotor. I had coils A and B energized together, or A and D energized, so that they will be the north poles and C and B will act like south poles. The other option is to interleave both the sequences. So, the first sequence will be switching on a single coil or energizing a single coil, and in the next step I will energize 2 coils, and in the third step again a single coil, in the fourth step 2 coils. So, you can see the movement here, how clearly when a single coil is energized it will point to that coil, and when 2 coils are energized it will take an in-between position between them. Similarly, in the third step this coil is energized, only that, in the fourth in between these 2. So, that is how it continues. You can see the positions shown here. So, first it will face coil 4, then in between coil 4 and 3, next only coil 3, then in between coil 3 and 2, and so on. So, finally, it will create 8 steps in the movement of the rotor. So, the continuation of that is shown here. So, next it will face coil 2, then in between 2 and 1, finally coil 1, and in between coil 1 and 4, and again the sequence is repeated. So, it has taken 8 steps to complete this sequence. That means the angle of rotation is still lesser. So, the angle of rotation will be higher when I use only 4 steps. When I use 8 steps, the step angle will be smaller. So, how do I energize the different coils? By sending a 1 from the microcontroller, I am going to send plus 5 volts on that line, hence that coil will get energized. So, normally the sequence used is a single 1. So, 0001, 0010, 0100 and 1000. So, when I use a one phase or wave drive system, a single coil will be energized at a time. So, a single 1 should be sent out of the microcontroller port. And if I use 2-phase excitation, this energizes 2 coils simultaneously. So, I am going to send 0011, 0110, 1100 and 1001 in sequence. It is a repetitive sequence, it goes on repeating. So, this is a high torque setup, whereas the first one is a It is a positional accurate setup. So, both these can be obtained when I use the half step interleaved sequence. In the third sequence, I am energizing 1 coil first, in the second step I will energize 2, in the third step again 1, in the fourth step 2, so on. So, I have a 8 step sequence in the last sequence, and this is how we are going to send the sequence from the microcontroller to energize the coils. So, now we should see what do you mean by step angle. It talks about how far the motor can move or the rotor can move within the shaft. So, the arc through which the motor turns with 1 step change in the windings. So, it varies from model to model of the stepper motor, and it depends upon the number of gear teeth present on the rotor or the shaft along with the stator. It is normally in degrees. This step angle can be defined as the total needed for one revolution is 360 degrees divided by number of steps per revolution. So, if I have 200 steps, I will get 360 by 200, which gives me 1.8 degrees would be the step angle. Is that clear? And if I have 100 steps, then I will give 360 by 100, which will give me 3.6 degrees is one step angle or one step which the rotor moves. So, the common step sizes are 500, 200, 180, 144, 72, 48, 24. How fast it moves? That speed is decided in revolutions per minute. So, how many revolutions we are going to have in 1 minute decides the speed. RPM is defined as 60 into total number of steps taken in 1 second divided by total number of steps per revolution. So, you can see in this the cross section of a stepper motor. You can see the central rotor having the teeth. So, there are many multiple teeth. For in the first step, when coil 1 was energized, it is pointing to coil 1, a particular teeth, and in the second step when coil 2 was energized, that teeth moves by a very small angle, and that angle can be 0.9 degrees or 1.8 degrees depending on how many teeth are present on this rotor shaft. So, if I have 25 teeth for example, then the movement here will be by 3.6 degrees. And when in the third step you can see when the bottom coil 3 is energized, the movement of that teeth or tooth will be by another 3.6. Here 3.6 when the energization changes from 1 to 2, again when energization changes from 2 to 3, another 3.6 degrees, so 7.2, and finally in the third step when coil 4 is energized, then another 3.6 degrees, so it becomes 10.4, and finally in the fourth step when it goes back from 4 to 1, another 3.6 degrees. So, around 14.4 degrees or something you will get the movement in one particular tooth of the rotor shaft. So, in detail we are explaining it here. The top electromagnet 1 is energized, attracting the nearest teeth of the gear shaped iron rotor. With the teeth aligned to electromagnetic 1, they will be slightly offset from electromagnet 2. If it is aligned properly here, it is offset here. In step 2, you can see it will be aligned, it will try to gain alignment with here, this electromagnet. So, when it is trying to gain alignment here, it will become a little offset here, by 3.6 degrees it moves. I am considering 3.6 degrees if I have 25 teeth on this rotor. And next in the step 3, this is energized. So, the same rotor tooth will try to gain perfect alignment here. So, here it will be offset by another 3.6 degrees and totally 7.2. Finally, when electromagnet 4 is energized, it will move by another 3.6 degrees. So, you can see that when the top electromagnet or electromagnet 1 gets energized after this, so it will move by another 3.6. So, totally 3.6 plus 3.6 plus 3.6 plus 3.6, 4 times it is 3.6 degrees. So, 3.6 into 4, that would be the total movement taken by one energize or one phase of energization of all the 4 coils and coming back to the original position. So, the teeth in the sprocket will have rotated by one tooth position. So, from this to this, one tooth position would have been completed, and if there are 25 teeth, for one revolution it will need 100 steps. So, just for one tooth position to changing from the center to the next, it will need 14.4 degrees. So, one tooth position has changed, and for this tooth position to complete one whole revolution around 360 degrees means it will take 100 steps. So, it needs to take 100 steps to finish one revolution. The common stepper motor types: universal stepper motor, where we have coil A, coil B separate here, coil C and coil D. The unipolar stepper motor, A and B are connected together with a center tapped common, C and D are connected together with a center tapped common. Finally, we have the bipolar where we have separate coils. Generally what happens, we cannot connect the output of a microcontroller directly to the stepper motor, because to energize those coils we need a high current. So how do I get a high current? The output current of microcontroller is very small, in the range of few milliamps. So how do I increase that current? To increase the current, you are going to make use of driver circuits. So driver circuits are those which will increase the current output of the microcontroller, so that current will be sufficient to energize the coils in the stepper motor. So it is an in-between connection between microcontroller unit and the stepper motor. So there are different types of drivers. We can have transistors used there. A pair of transistors, we call them as Darlington pair, or you can use arrays of Darlington pairs. This is how it is. You can see two transistors connected back to back like this will give a very high current gain, and it is used in common collector configuration. So remember, common collector configuration of transistors gives us the maximum current gain, but voltage gain is 1. So there is no change in voltage, but only the current will be increased. That is what we need here. So output voltage of the 8051 should remain the same, only current level should be increased. That is provided by connecting the transistors in common collector configuration, and if I use a single transistor, I will get only a very small increase in current. When I want very large values of current, I will use a pair of transistors connected together known as the Darlington pair. I can also use diodes, or let us say transistor inverter circuits, as you can see here. So this IC is called ULN2003. This is the driver IC. How do I connect the stepper motor to 8051? This 8051 port 1 is used. In our current example, I am using port 1 of 8051. I need only 4 lines of that port, 1.0, 1.1, 1.2 and 1.3. All these 4 lines will be connected to the driver IC first to increase the current level, and we also use these resistors. They are called pull-up resistors. So they will be helping whenever I connect a driver, and then I am going to connect the output of the drivers to the coils. Coil A, coil B, coil C, coil D. All the 4 coils need 4 wires from the motor driver. The common points are connected together and they are given to 5 volts. So these are the center tapped commons from both the coils, and they are given to plus 5 volts. This is the rotor shaft. Okay. So you have to remember this diagram and write this whenever they ask for stepper motor interface. How to connect the 8051 to the stepper motor. So this is the kind of connection. The same thing is shown with a block diagram of, we just call these power amplifiers rather than drivers. It could be either way. It is a block diagram approach. So we have also connected a PC where we can run the Keel compiler, so that you can write programs in C. Rather than assembly language, the program can be written in high level language or the C language when you connect it to your PC. So the sequence is as shown before. I had already shown you the sequence which will be sent from the microcontroller on the port lines, port 1 lines, 100, 0100, so on. This is when I am using single coil excitation at a time. If I want to move the motor in the clockwise direction, I will start the sequence with 1000. If I want to move the motor in the counterclockwise direction, then we will start it from 0001. So how you begin the sequence depends on whether the motor moves in the clockwise direction or counterclockwise direction. So it is a single step excitation sequence. In the second one, I have shown 2-step excitation sequence. In the third one, I have shown the interleaving between the single and two-step excitation sequences. So, we have already considered all these sequences, and just all what you have to remember here is, if we have to move it in the clockwise direction, you should give it in this order from top to bottom. The sequence should be sent to the port 1 bits of the microcontroller. If you want to move it in the opposite counterclockwise direction, then you should send the excitation sequence in the reverse order as it is shown in this arrow. So, what is the algorithm? Since we are not familiar with the assembly level language of 8051, we just need to define the program what we write in terms of steps or algorithms. We call it as an algorithm. Once we start the microcontroller and the stepper motor, it is powered on. Start means power on. Then connect the 4 stator windings to the port 1 bits through the driver circuit. You use a driver IC and connect it as shown in the figure. Power up the motor. Then send the initial excitation sequence as I have shown in the previous cases. If I want single coil excitation, I will send the sequence 09, 90 or 99. I need only 4 bits, but why take risk? I will send 9 on the 4 bits, the higher 4 bits of the port also, and then introduce some delay. So, before I send the next excitation sequence, I will introduce a small delay depending on what RPM we need. Now, you change the excitation sequence. So, in the first set, the motor would have moved a little, say by some angle 1.8 degrees or 3.6. Now, after the delay, if I change the excitation sequence, the motor moves one more step, and that is how it continues. Stepwise it is going to move. It can move by 200 steps for one revolution or 100 steps for one revolution, all that. And for the anti-clockwise direction, if I want to move it in the anti-clockwise, I will change the excitation sequence in the reverse order, and this is the end. So, this is how we are going to program the microcontroller for stepper motor interface. The applications are, it is used in instrumentation, especially watches. If you would have opened your watch behind, you would see the stepper motors. You can see 3 different motors moving there. Each one is for second, minute and hour. So, you will have the rotation controlled through such motors. Clocks, they all use these stepper motors commonly. We use it in computer peripherals like card readers, teletypes, teleprinters, dot matrix printers, robotics to control the movement of wheels of the robot, any toy cars, everything. These are the various applications. So, this completes module 4. The general questions in module 4 are architecture of the microcontroller, its specific features and the stepper motor interface. These are the 3 things. In flip-flops and latches, we have already discussed the questionnaire. So, with this I will wind up my sessions. Thank you. Thank you for your patience.